welcome to class. My name is Professor Don. In this class, we are continuing our conversation about IPv4 addressing. You should already have watched part 1 where we talk about the basics of IPv4 addressing. This video talks about subnetting specifically, and there's a third part that talks about variable length subnetting. This video should help you understand the next video, so make sure you watch this whole video. And the last video, part 1, should help you understand this video, because I'm not going to go in depth in IPv4 addressing, only how to subnet in this video. So let's go ahead and get started. If you have any questions, please ask your questions inside of our help discussion forum. And if you're taking this class live with me, if you're watching the video in YouTube, ask your questions inside of our help down below in the help comments, and I will do my best to answer those questions. And if you are live with me now, which I know none of you are, but if you were live with me, I'd ask you to hold your questions to the end of the presentation. All right, almost there. Let's see from the beginning. And all right, everything looks right. All right, here we go. Module 11, IPv4 addressing part 2. Now, in our part 1, we described the first 3 topics, describing the structure of IPv4 addressing, comparing characteristics and uses of an IPv4 addressing, including unicast, broadcast, and multicast. We also talked about public, private, and reserved IPv4 addressing. That we covered in module 1, my first video, not module 1, part 1. This video, we're going to explain how subnetting segments a network to better enable communication, to enable better communication, and we're going to calculate IPv4 subnets or /24 sub prefix. We'll also talk about 8 and 16 briefly, but we really get into just the 24 because that's what's testable in this course. So many protocols use broadcast or multicast. For example, ARP uses broadcast to locate other devices, and hosts send DHCP discover broadcast to locate a DHCP server. Switches propagate broadcast out all interfaces except for the interface on which it was received. That creates a problem because the only device that stops a broadcast is a router. Routers do not propagate broadcast. That's a good thing. We don't want our private addressing getting out to the internet. Each router interface connects to a broadcast domain, and broadcasts are only propagated within that specific broadcast domain. But if you have a large domain, there's a problem. The problem with the large broadcast domain is that these hosts can generate excessive broadcasts and negatively affect the network. The solution is to reduce the size of the network to create smaller broadcast domains in a process called subnetting. Subnetting allows us to divide a given network address, for example, 172.16.0.0/16, into two subnets of 200 users each, 172.16.0.0/24, and a second network, 172.16.1.0/24. Here in the first picture, I'll zoom in on it. Here in the first picture, we have one domain with 400 users and a bunch of switches that are broadcasting. Remember, every switch broadcasts every received packet out of all ports except for the incoming port. It would be better to separate LAN 1 and LAN 2, whatever they are, HR, students, teachers, administration, sales, into 2 different users. That way, we have smaller subnets, we have smaller domains, we have ultimately, let me fix my camera a little bit here. we ultimately have less problems if there is something like a broadcast storm, which creates a problem in this network. It wouldn't affect this network at all. So it's good to segment networks. That's what this slide is for. Now, subnet, the reasons you segment networks, subnetting reduces overall network traffic and improves network performance. It can be used to implement security policies between subnets. Subnetting reduces the number of devices affected by an abnormal broadcast, as I just mentioned. Subnet schemes are assigned for a variety of reasons, including, say, by location. So each floor has its own subnet, or group or function here. So we have administration, and we have human resources, students, faculty, or accounting. We could do it by device type. So you could have one for all hosts, another subnet for all servers, a third subnet for all printers, for example. So your decision why you subnet, we subnet for smaller broadcast domains. How you do that is really just your decision. Subnetting an IPv4 network. Networks are most easily subnetted at the octal boundaries of 8, 16, and 24. It doesn't have to be, as we'll see at the end of this presentation. Subnets are created by borrowing host bits for network bits. Now, every now and then, instead of using the term borrowing, I use the term taking, because you don't ever give those bits back. Once you take a host bit and give it to the network side, ultimately, that now you have, for example, if you take one host bit, you have now two networks, right? If we were subnetting on a /24 network, and you take one host bit, now you have two networks of 128 addresses, 126. Two networks of 128 addresses, 126 usable. If you take a second host bit, then you have four networks of 64 addresses, 62 usable. We'll get into that more deeply as we go, but I do like the term taking instead of borrowing, because you never give them back. More host bits borrowed, the more subnets that can be defined. Note that using longer prefix lengths decreases the number of hosts per subnet. So what they're saying there is, if you have a /8 to start with, then you only have so many networks and lots of hosts, right? You got 16 million. If you were working with a /8, you have 16 million hosts, but you have fewer networks, right? We have 2, 4, 8, 16, 32, 64, 128, 256 networks of 16 million addresses. If you have a /16, we have an even amount of both. You actually end up having 65,535 networks of 65,535 hosts. And what we'll see a lot in this course, because it's what we train with, is a /24 network. That gives you 24 host bits and 24 network bits and 8 host bits. So it doesn't really matter which network we're working with, whether we're working with this octet or this octet or this octet. Ultimately, subnetting works exactly the same in each octet. You just end up with more hosts. If you borrow a bit here, you get if you borrow a bit here, you get two networks of 8 million addresses. If you borrow or take a host bit here, you get two networks of 32,000 whatever, to 32,700 something. And if you borrow a bit here, you get two networks of 126 usable. These are usable hosts, but there's 126 IP addresses in a /24. All right, so that's enough of this slide. Let's go on to see what else we can learn. So octet boundaries. When we're talking about subnetting at the octet boundary, we are working with subnetting that second octet and a /16, a /20, Well, here they're only talking about a 16, and you can see what I was just talking about where a lot more addresses. Well, it's possible because here you have 250, here you have 256 possible networks, and they show it, 256 networks, and each network has 65,000 hosts per subnet. Notice the numbers are 10.0.0.1 through 10.0.255.255.254. One more is the broadcast. Then you go to the next network, 10.1, all the way to 254. Then you go to the next network of 10.2, each with 65,000 with broadcast. They layer that as well, all the way down to the last network of 255 addresses. So, for example, if you were subnetting a 10.x00/16 and define up to 256 subnets, the first two octets identify the network, and all the rest are IP addresses. Now, here we take that challenging concept that we just got, and we break it down to something you should understand, you have to understand, to be able to do well in subnetting in your Cisco 1 class. So here we have a /24, and notice the networks are 0, 1, 2, all the way up to 10.255.255.0.024, taking it from 1 to 254. Each range of hosts is only 256 addresses, 254 usable, the network address, and then the broadcast address at the end. Okay, so this would give you 16,777 216 subnets. That's why they say it's easier to subnet just doing it on the boundaries. Now, within an octet boundary, and again, we're just going to work with the /24, it's the easiest to understand. When you take a host bit and give it to the network portion, you increase the number of network bits. So we go from a /24 to /25. Remember, the /24 is just 24 ones in the subnet. You can see that here, 24 ones, 8, 16, 24. We take a network bit, a host bit, we turn it into a network bit, borrowing. And now we have two networks of 128 addresses, 126 hosts, the network address and the broadcast address. Take another network bit. Now you have 26 host bits, and we have 4 subnets of 62, actually 64 addresses, 62 usable. Split it again, we have 8 of 32 addresses, 32 host bits, network bit, and a subnet. We have 8 networks at a /24 if we had equal size. You'll learn later that you can have multiple sizes. That's variable length subnetting. So you can have 125, 227s, a 30, and 29 and 430s if you want. But in this presentation, we're just subnetting in equal size subnets. So borrow 1 bit or take 1 bit, you get 2 networks of 128. Take another one, you split it in half, you double the networks, you half the host bits. Take another bit, you double the networks, half the host bit, half the IP addresses, again and again, all the way until you get to /30, which is 64 networks of 4 addresses, 2 usable. Now, we don't use a /31 when we're working in the 4th octet, but you do use the 7th and 8th positions when we're working in the 3rd octet or the 2nd octet when we're subnetting. If you are working within the 2nd octet or if we're subnetting in a /8 or a /24, then you do use the 31, which is 128 addresses, but here we never have anything that we never use less than 4 addresses when we're implementing a network in a Cisco router. We always need 2 addresses. For example, point-to-point networks, sometimes called connecting networks, always use an IP address on each side of the router connection, and then you need the network address and you need the broadcast address. So the least we can use is a /30 for those 4 addresses. But if we're in a different octet, then you can go to /31. It actually wouldn't be 31, but you could break it down into that 7th bit and then the 8th bit. Now /32 means 1 address if we're subnetting in the 4th octet. That's what, if you have 32 bits set, that means all bits, which means 1 address. And you see that in a routing table. I'm sure we already looked at it. If not, we will soon. All right, so let's go to the next slide. I have a video here that's going to talk about the subnet mask and how we subnet in binary. Now, earlier in a previous class, we talked about ANDing, and that's converting IP address and subnet mask into a network address, basically logically ANDing the ones between the two. Only a 1 and a 1 equals a 1, everything else is a 0. And the result gives you the actual network address. Here, let's go ahead and watch the video, and I'll follow up with the video in just a moment.
Now, I want to take a moment to point out that subnetting makes sense from the binary perspective. In other words, when we take the IP address and the subnet mask and convert them to binary, I have the IP address on this row here, I have the subnet mask on this row, converted to binary, that the computer and the router are able to logically AND or combine the IP address and the subnet mask and find the network address. In other words, this ANDing process is a logical process of ANDing. So a true and a true makes a true, 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 false and a true makes a false. And if we do that and logically AND the IP address with the subnet mask, we get the network address. So 192.168.1.10 logically ANDed with 255.255.255.0 produces the 192.168.1.0 network. This is at the core of the IPv4 address and subnet mask and subnetting in general. What about non-classful subnet masks? We've seen that the class C subnet mask is /24. We've seen the class B subnet mask /16 and the class A subnet mask /8. But what if we use classless masks? In other words, what if we have a /25 subnet mask or a /18 subnet mask, creating a 255.255.192.0 subnet mask? Or for that matter, a /12 subnet mask, 255.240.0.0. How does that work, and how does that change the networks that are created by the combination of the IP address and the subnet mask? This is called subnetting. I'll explain it using an example scenario. Let's start with a classic Class C network like 192.168.1.0 with a /24 or 255.255.255.0 subnet mask. If we want to subnet this 192.168.1.0 network, what we need to do is go into the subnet mask in binary, which we can see on this row right here. And what we do is, to change the subnet mask, we borrow bits from the host portion of the address. This is done from left to right. So I could take this first 0 here on the left and change it to a 1. And now I've effectively changed the subnet mask from /24 to /25. In other words, if I convert this back to decimal, it's now 255.255.255.128. This completely changes the nature of the network. we now have a /25 subnet mask, and we only have 7 host bits. So starting from a /24, we now have borrowed 1 bit from the host portion. We call this 1 bit a subnet bit. If we look at it from the perspective that we started with /24, we've added 1 bit. So we could say that subnet bits, we now have 1 bit, or 2 to the first power, creating 2 subnetworks. Host bits, we have 7 zeros now. So host bits are 2 to the 7th power, or 128, minus 2 for the network address and the broadcast address, leaving us with a total number of possible hosts on the subnets of 126. So by borrowing 1 bit from the host portion of the address, we create 2 subnetworks, each subnetwork with 126 hosts. The subnetworks are the 192.168.1.0/25 subnetwork and the 192.168.1.128 subnetwork /25. We can prove that this is the case using logical ANDing to prove how the router or a computer would take an IP address with this particular /25 subnet mask and derive the resulting network address. In other words, let's put in a host address. I'll put in the host address here, and I'll say, let's put in the address 68. So I changed this to a 68. So now we've got host 192.168.1.68. So this needs to be a 1. That's the 64. And then we need to add the 4-bit here. So now we have 68. If we logically AND the IP address here with our new subnet mask /25 here, let's see the result. We'll get a 1, a 1, a 0, 0, 0, 0, 0. So that's 192. And then here, the result is 101, 01, 168. And then all zeros here and a 1. This is a 1. And now, if we look at this last octet, a false and a true makes a false. A true and a false makes a false. And then we get all zeros here. So the address, the network address, is the 192.168.1.0 network. So host number 68 is on the 0 network. Well, this makes sense because if the next subnet is 128, if we put in a host address larger than 128, we'll see if it falls in this subnetwork. So let's change it slightly. I'll change the host address to 138. So now I'll change this, put that as 0. So there's a 128 bit. I'll make this a 1. I'll put a 1 here. So 128 plus 8 plus 2 is 138. If we do the ANDing again, we see that a true and a true makes a true. And then we have falses all the way. And now the resulting network address is 128. So when we take the IP address with the /25 subnet mask, we see that the network address is 192.168.1.128. So we've created 2 subnetworks from the single 192.168.1.0/24 network. We've created 2 subnetworks. The subnetworks go from 1.0 all the way up to 1.127, with 0 being the network address and 127 being the broadcast address. And the second subnetwork starts at 128. So this is the network address because it's the first address, all the way up to 255. And since this is the last address, this is the broadcast address. In other words, the first address in the subnet is the network address, and the last address in the subnetwork is the broadcast address. This process is called subnetting.
Okay. Hopefully that was helpful. Of course, those videos are also located in our NetAcad classroom, so if you want to see it again, you can. Again, the key here was we took one network, we borrowed one bit, took one bit. He actually even said take a bit. So he took one bit and that created two networks. And then he showed you how the networks broke out to be 0 through to 127 and then 128 to 255. 0 and 128 of the network addresses, 127 and 255 of the broadcast address, leaving 126 addresses for host bits. Nice and simple subnetting with just borrowing one bit. Okay, here's a video demonstration because obviously we want different combinations than 128. So we need half of that 64, half of that 32. But how can you wrap it all together to determine the subnets, where they start, where they end? By the way, I don't use the term magic number. It is useful. The magic number, the place value, first place, second place, third place. This is 128, 64, 32. I like to call those block sizes. He doesn't mention block size in the video, but I like to term those block sizes because those are the blocks of the network size in blocks of 64, blocks of 32, blocks of 128. Anyways, let's watch the video and see how he explains it.
This video focuses on subnetting and how to find your subnetworks easily and quickly using the magic number trick. Let's say we're subnetting a 192.168.1.0 network /24. I have the IP address and subnet mask in decimal here, and I have them listed in binary here, the network portion of the subnet mask and the host portion of the subnet mask. To subnet this network, what I can do is I can borrow one bit from the host portion of the subnet mask, and now I have one subnet bit. This changes the subnet mask from /24 to /25. If I borrow one bit from the host portion, I have one bit, or 2 to the first power, makes two possible subnetworks. The subnetworks I've created are the 192.168.1.0 subnet and the 192.168.1.128 subnet, both /25. The hosts on each network are 126 usable hosts. We have 7 zeros here, and 2 to the 7th power is 128, minus 2 makes 126 usable hosts per subnet. If I decide to borrow 2 subnetwork bits from the host portion of the original 192.168.1.0/24 network, I now have /26. I've borrowed 2 bits, so now I have 2 to the 2nd power of subnet bits. So I have effectively 4 subnetworks. The 4 subnetworks are listed here. For host bits, I have 6 zeros in the host portion of the address, and 2 to the 6th power is 64. Minus 2 for each subnet makes 62 usable hosts per subnet. The subnetworks that are created are the 192.168.1.0 subnet, the 64 subnet, the 128 subnet, and the 192 subnet. Notice how the number of borrowed bits and the number of host bits determines a lot about the subnet. If I borrow 3 subnetwork bits, I now have a /27, so it goes from /24 to /27. I have 3 subnet bits. 2 to the 3rd power is 8. 2 times 2 times 2 is 8. And you can see that I now have 8 subnets, or 8 subnetworks, created from the original 192.168.1.0 network. Each subnet is now /27. Notice that there are now 32 hosts, or 30 usable hosts per subnetwork. We could go up to /28 And now I have 4 subnetwork bits. Notice that the subnet mask has changed from 255.255.255.0 when it was /24 to now 240. I now have 16 subnetworks, or 2 to the 4th power, and there's 2 to the 4th power of hosts per network. So there's 16 or 14 usable host addresses per subnet. Borrowing 5 bits looks like this, and borrowing 6 bits looks like this. I've now borrowed 6 bits from the original 8-bit host portion of the original /24 network, and I now have 2 to the 6th power of possible subnetworks, meaning I have 64 subnets. The host portion of the address is now only 2 bits, or 2 to the 2nd power, meaning there's only 4 host addresses per subnet. Now, if you have 4 host addresses, you have to leave room for the network address and the broadcast address. So 4 minus 2 leaves only 2 usable hosts per subnet. Typically on a LAN, we do not go higher than a /30 subnet mask. Otherwise, you'll not have enough room for usable host addresses. In other words, we can't borrow any more bits from the host portion, or we won't have enough addresses for hosts. You might be asking yourself how I was able to discern the different subnetworks from the subnet mask or subnet bits that were borrowed. There are many different ways to derive the subnetworks from the subnet mask, but my favorite is the magic number technique. The magic number is simply the place value of the last one in the subnet mask. So in this situation, we have a /25 subnet mask. We have 25 ones, and the last one is the one here all the way on the right, highlighted in red. This one, if we look at it according to this octet, is in the 128th place. If we think about the place values of 8 bits, this is the 128th place. So the magic number in this situation is 128. The magic number tells us where to find the networks. It tells us that the networks will go up by 128. So in this case, the first network, which is always 0, so 192.168.1.0/25, and from there, the networks go up by 128, so the next network is 192.168.1.128. Let's see how this works, borrowing 2 bits from the host portion. Now I have borrowed 2 bits from the host portion of the subnet mask. The magic number is now the last binary 1, which in this case is in the 64's place. So the magic number is 64. The magic number tells us how to find our networks and lets us know that the networks will be going up in increments of 64.
I just want to pause the video just for a moment here, just to state that this trick he is showing you shows you the size of the blocks. That's what I use, but he uses the magic number. But it shows you the size of the blocks. This trick works in every octet. So by looking at the position of the host bits here that have been borrowed, taken, in the 3rd octet or in the 2nd octet, you can find out what the block size is and the numbers, such as 192, for example, for the 2 bits taken, 128 for 1 bit, 224 for 3 bits, 240 for 4 bits. That works in the 3rd octet, the 2nd octet as well. Now, he doesn't go in depth in talking about the 2nd and 3rd octet in this video, but I just want to tell you that this magic number trick works. Just look at the last host bit, the last network bit, and whichever octet you're in, and then convert it. Think about it in the place notation, if you will, and that will tell you the block size of your networks. All right, go ahead and let him finish.
So for instance, The first subnet is always 0, so 192.168.1.0/26. The next subnet is 64. 64 plus 64 is 128, and 128 plus 64 is 192. You can see how the subnets are going up by 64. There's only 4 subnets because we've borrowed 2 subnet bits. Also, we can go no higher than 192 because 64 plus 192 is 256, and that's too large a number. Let's see how it works with 3 bits. With 3 bits, we now have a /25, 26, 27 subnet mask, /27 subnet mask, in decimal 255.255.255.224. The last one in the subnet mask is our magic number. In this case, it's in the 32's place in the binary conversion table. So the magic number is 32. If we look at the networks, we'll see that they go up by 32. The first network being 0, 192.168.1.0/27. Then the 32 subnet /27, 64, 96, 128, 160, 192, and 224. The subnets go up in increments of 32, following the magic number. Now that we see the pattern and how the last borrowed bit affects the location of the subnetworks, let's try it with a /28 subnet mask. Now I have the 192.168.1.0/24 network. I want to subnet it, changing it to /28. /28 means I borrow 4 bits in the subnet mask. So I now have 28 ones counted from left to right. 255, 255, 255, 240 subnet mask. 128 plus 64 plus 32 plus 16 is 240. The last one is in the 16's place. This is the 128's place, the 64's place, the 32's place, the 16's place. So the magic number is 16. We'll see that the networks go up by 16. The first network is always 0, so 192.168.1.0/28. I'll copy this and paste it, and the next network will be the 16 network. Why? Because the magic number is 16, because the last one is in the place value of 16. The next network will be 32. And the following network will be 48. And after 48, 64, and so on and so forth. The networks will go up by 16. In each network, we have the host bits, 4 bits for hosts, which is also 2 to the 4th power of 16. So the network will go from 0 up to 15, with 0 being the subnetwork address or network address, and 15 being the broadcast address. And the next subnet is the 16 subnetwork. Now let's try creating /29 subnets. We can see that that involves borrowing 5 bits from the host portion of the subnet mask, and that the last one is in the 8th place. So the magic number is 8. The networks will go up in increments of 8. So starting from 0, we'll have the 8 network and the 16 network and the 24 network, and so on and so forth, all subnets being /29. For the /30, we see that the last one is in the 4's place, and that the networks will go up by 4. So similarly, the networks will go up in increments of 4. So the first network is the 0 network, then the 4 subnetwork, then the 8 subnetwork. Each subnetwork will have 4 host addresses, in this case 0 to 3, 0 will be the network address, 3 the broadcast address, and the addresses between 1 and 2 will be the usable host addresses. Only 2 usable host addresses in a /30 subnetted network. You might ask yourself, will this technique, the magic number technique of looking at the place value of the last one in the subnet mask, work in other subnetted octets? In other words, if we're starting from a class B /16 network address or a /8 class A network address, would this technique work? And it does. For instance, if we take a 172.16.0.0 network /16, you can see in this scenario, I've subnetted it to a /23 subnet mask. In other words, I've taken the original 16 network bits and borrowed 1, 2, 3, 4, 5, 6, 7 ones from the host portion of the subnet mask. In this situation, the last borrowed one is in the 2's place. So the magic number in this situation is 2. This means that the subnets will go up by 2 in this octet here. So in other words, our first subnet will be 172.16.0.0/23, and the next network will be 172.16.2.0/23. The only difference is now, instead of 16 host bits like we would have had in a /16 network, we now have 9 host bits. So 2 to the 9th power, meaning we have 512 minus 2 would be 510 host addresses that we can assign. In other words, the network goes from 0.0 all the way up to 172.16.1.255. So the first usable host address would be 0.1, and the last usable host address would be 1.254. The next subnet starts at 2.0. After that, the networks continue to go up by 2. In other words, the next subnet will be the 4 subnet, and then the 6 subnet, and the 8 subnet. Notice that the networks are going up by 2, but in the 3rd octet, not in the 4th octet. The only difference not to be confused on is the larger number of host addresses that you'll experience when you subnet in this octet or in the 2nd octet. You can see how the magic number technique can help you quickly locate the networks or subnets.
So we did touch on the 3rd octet and the magic number block size working in the 3rd octet. What I was thinking, and when I mentioned it earlier, was he doesn't really explain it when it comes to multiple octets or something on a non-boundary. So it still works if you have, say, you're given a /10 or a /22 address from your ISP. You can still subnet it. It works the same exact way. You still look at the position to determine the block size, but the positions are different because you're starting with a different position. I'll explain that coming up in a little bit. So we'll get there in a minute. Hopefully that video was helpful. And again, it's the last bit that you're looking for to decide the block size. And once you decide your subnets, in this case, we've taken one address. Looks like we started off with a 192.168.1.0. Nope, that's the 25. Let's see, what do we got here? We have, let me get out of the Zoom mode. They have created a 128. So they must have started with 168.1.0. That's Yeah, 1.0, there you go. And then they split it to a /20. That should be 24 right there. That's a mistake. This should be 25 here. The first usable address they've assigned to the router, .1, .2 is to the PC, and then in the 1.128 network, no, I guess it is. I guess it is. They're just not showing you the original network here. So this is 128/25. So it started with a 1.0 slash 24, and they subnetted into two addresses. So this is the first usable 129. You don't have to use the first usable address on a router, but that's common in this classroom. And then the second usable was on the PC. And then you just go into the IP settings. We've done this in class many times in the past, setting our IP address, and of course, make sure you add the default gateway. That's how you assign IP addresses in a PC and in a router. Just go into the interface, IP address. You've done that before already. Creating two equal size subnets. This is what he actually just showed you. Starting at, here we go, starting at 192.168.1.0/24, borrow or take a bit. That bit is magic number 128. So the block sizes are 28. So you're going 168.1.0 to 127, 128 to 255, and that gives us your range. So that's how G00 ends up being 192.168.1.1 for G00, and down here 192.168.1.129. That would be this address right here. All right. You're going to do a packet tracer where you're going to subnet an IPv4 network. Now, you can also subnet a /16 with a /8 prefix. It just means you're subnetting in the third or second octet. They talked about it before. If you have a /16, you have, 65,000 addresses. So if you borrow or take one address, now you have two networks of 32,000. Take two network addresses, you have four networks of 16, 8 networks of 8, 16 networks of 4, all the way down. Remember earlier I said, when we're down here at a /29 and a /30, we don't go to this low number. But of course, if you're starting at 16, then you absolutely can go to the 7th position, which would be a /23, in this case 128, with 510 addresses, half double the networks, half the host. Now the interesting thing here you're seeing for the first time is you subnet from wherever you begin. So we started with a /16. So /17 is two networks of half the number of hosts. So a /16 has 65,500 something. So a /17, if you subnet to 17, you get two networks of 32,000. 18 is four networks of 16,000. 19 is 8 networks, right? So that shouldn't be too, and therefore, when you get to /24, 25, 26, it's not the same 2, 6, 8. No, that it just continues. So if you go from a /23 to /24, but you start at a /16, and you go from a 23 to a 24 to a 25, you're going from in the third octet, 252, 64 networks of 1,000 addresses. The 7th position is 1, 2, 3, 4, 5, 6. The 7th, where's my mouse? The 7th position, 254, 128 addresses of 510. The 24th position, the 8th position, you have 255. which is 256 address networks of 256 hosts, 256 IP addresses, 256 hosts. So it really matters where you begin with. And we'll see that on the very last slide. Here they show it again. They're just showing, this a little confusing, but let's say you have a large enterprise and you have 100, you need 100 subnets to be able to hand out to all of the networks. You could get there if you start with the /16. We could never get to 100 subnets if we start, let's see, can we do that? Well, we wouldn't have any addresses. You could, if you have, no, you can't get to 100. If we were in a /20, started with a /24 address, and you subnet all the way down to /30s, you still only have 64 networks of 4 addresses, right? So you could never get to 100 subnets. So you would need to start earlier. You would have to ask the IP for a /20, a /16, /8. You know, they probably want to give you an 8, but you get the idea. So when you start with the 16, then you could subnet. You take 1 bit. You got 2 networks. Take 2 bits. You have 4 networks, 3 bits, 8 networks, 2, 4, all the way down. Now we could stop here because we need 100 subnets. So we can stop at 7 bits. We can stop here, and we get 128. And if you were to play that out here, up here, that's that guy right there. Oops. You would read that as 128, 96, 224, 240, 248. Let's see, it's tough for me to do in the middle here. But anyway, so you would just add up the positions. So 128 plus 64 is 192, plus 32 is 224, plus 16 is 240, plus 8 is 248, plus 4 is 252, plus 2 is 254, plus 1 is 255. We only needed it to the 7th position, which was 254, okay? And that would give us 128 subnets. We would only use 120 of them. And we do the same thing. Again, if you needed 1,000 subnets, you would have to start with a /8 to be able to get there. And actually, notice we actually subnet into or across multiple octets. You needed to actually borrow, let's see, 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 1,024 networks is this host bit here. Now the magic number is 128. This is 64. So there would be block sizes of 64, but we in a slash. But we would be a slash, let's see, a slash, we're taking network bits, so 8, 16, 17, 18, a /18, starting with the /8. All right, here's a video demonstration of that, subnetting across multiple octets. The challenge here was to create over 300 equal-sized subnets of 20,000 hosts each. Now, there's where the challenge is. 300 octets, 300 subnets isn't that challenging. We've seen how we can do that, maybe even in the 3rd octet, but with 20,000 hosts. So we have to be talking about the 2nd octet to have that many hosts in any octet. So we're starting from the 8, from a /8. Let's watch the video.
In classless subnetting, we've seen how we can borrow bits from the host portion of the subnet mask, and that the last one that's borrowed is the magic number, meaning that the last one, if we look at the place value of the 8-bit grouping, the last one in this case is in the 32's place. So the networks go up by 32. Starting with the 0 network, we have the 32 network, then the 64, 96, 128, so on and so forth. But the networks go up by 32. What about when we're subnetting from a Class A or Class B network address and subnetting generally in the other octets? Let's take a look at another example. This time we have a 10.0.0.0 network address and a classful Class A subnet mask, and we're going to subnet it. So we've taken the 8 bits and borrowed 3 bits, and now we have a /11 subnet mask. The last one in the subnet mask is still in the 32's place. If we look at this 8-bit grouping in this octet right here, the last one is still in the 32's place. So the networks will go up by 32. So the networks are the 10.0, 32, 64, 96, and they're going up by 32, but in the second octet. The only difference is now we have a lot more host addresses. We have 8, 16, 21 zeros for hosts, which means there's over 2 million hosts per subnet. For instance, if we take a look at this 10.192.0.0 subnet, the next subnet is 10.224. So that means that the host addresses go from 0.1 all the way up to 10.223.255.254 as the last usable host, and 255 is the broadcast. The next address is 10.224.0.0, which is the next subnet. All of these subnets are now /11. What about a more difficult scenario? In this scenario, we need to create over 300 equal-sized subnets of 20,000 hosts each, starting from the 10.0.0/8 network. So we need to create a lot more subnets, and we need a lot of hosts. Looking at this situation, we know that we're going to need to borrow bits from the host portion of our subnet mask. The question is, how many bits will we borrow? If we borrow 1 bit, we have 2 subnets. Now we have 4 subnets, 8 subnets, 16, 32, 64, 128, 256, 512. If we borrow 9 bits, we'll have 512 subnets that we create, and that will be sufficient to meet the demand for 300 equal-sized subnets. What about the requirement of 20,000 hosts each? We have 15 zeros left for hosts per subnet. 2 to the 15th power is 32,768 minus 2 would be 32,766 hosts per subnet. That meets the requirement of having at least 20,000 hosts in each subnet. So this scenario would work. You can see here that I've now highlighted the borrowed bits from the subnet mask. I've also converted it to decimal here, 255.255.128.0. And I've already ascertained that the last one in the subnet mask is in the 128's place, so the magic number is 128. The subnets will still go up by 128, but they'll also need to go up for every number possible in the second octet. If we look below here, we can see our subnets. The first subnet will be the 10.0.0.0/17 subnet, then the 0.128 subnet, then the 1.0 subnet, then the 1.128 subnet. And as you can see, we're iterating through every possible number in the second octet, and then going up by 128 in the third octet. If I was to list out every possible subnet, we'd go all the way up to 10.255.0.0, and the next subnet would be 10.255.128.0. /17 is our last subnet, for a total of 512 subnets. In a situation like this, there's many more subnets and many more hosts per subnet, but the rule of the magic number still applies.
All right. So if you understood that, you understand subnetting, and you're gonna do a lab on this to calculate IPv4 subnets. Make sure you actually do this lab. Don't just look up the answers online, because this is what you're going to need to do when you're working for your CCNA exam. Now, a couple more slides talking about subnetting to meet requirements. A couple examples. So, subnet private versus public IP address space. So enterprises will have an intranet. That's the private IP addresses that you will use, and you'll probably use maybe a 10.0.0/8 network and subnet on the 16 or 24 boundaries, just to make it easy. There will also be a DMZ. These will be public addresses that should be accessible from outside of the network, from the internet. And the DMZ would have to be configured with probably static public addresses to be able to be, like I said, accessed easily. Now, I guess it is a way to map those addresses using NAT, and you'll learn that in Cisco 2, how to go about mapping an address to a server inside of a DMZ zone. Probably public addresses, but subnetted out of the network that is given to you. Now, there's two considerations when planning subnets. Remember, that last video was the best because you got to determine the number of networks. In that case, you needed 300 networks, and the number of hosts. We needed 20,000 hosts. You needed a lot of both, and and you saw how he was able to complete that task. Again, in this class, we're just going to work with the fourth octet, a /24 network, so it shouldn't be too challenging. If you can pretty much memorize this table, took me a little while to do it, but if you can memorize this table, you'll be good to go. Now, you can you subnet based on network requirements. So you decide, as we started out this presentation, you decide how to network. Do you break it up with HR and sales and tech support and executive administration? You decide how to break it all up. It's really based on you. In this case, we're going to use categories, and we're going to break those categories, showing in this diagram the number of hosts needed in each one of those categories. So we get engineering, human resources, sales, tech support, and executive management. The challenge being here that, first of all, how many networks do you have? Easily, all of you will see the 5 networks we have here, but do you see also the 4 connecting networks? So we have 4 connecting networks. Each of these have to have their own IP address, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 networks that we need. So right off the bat, interesting enough, starting with the /22, we need to have at least 9 networks. Now, if you remember our numbers there, that would be borrowing. Let's see, if we go to 23, we have 2 networks. 24, we have 4 networks. 25, we have 8 networks. 26, we have 16 networks, and that's what we need. We need to stop there. So we have a 26 as our subnet mask, /26. That gives us 16 networks, and they show you the 16 networks here, 0 through 15. Then they also break down the bits that we borrowed. We borrowed these 4 bits, so that's what gives us our 16 networks. And by borrowing the 4 bits, we also leave ourselves a number of hosts that we have. So we have 2, 4, 8, 16, 32, 64. So notice our addresses go up by 64 in the example that they give here. And notice that just like in the video with the 300 and 20,000, For every network in the second, from the third octet, we go, the 16 octet, all 0, all 1, all 2, all 3, all the way up to 255. That's not true. 16.3.192 before you go roll into the next network. So, because that's where we are here. And that's a /26. Here we've laid it out and actually put the IP addresses in note. We've given IP addresses to each one of the connecting networks. This is a challenge, a /22, because students, I put it on the next screen, students will not think to start with 22, giving of one network a /22, going to, let me change my pointer here so I can make this more clear. So you start with the /22. Your ISP gives you a /22. That's what you have to work with. So you split a 22 into 2 23s, 4 24s, 8 25, 16 26s. And since you have a /22 has 1,024 addresses, so you split them. When you get twice the network, you split the address on and on all the way down to 64. Now this gives you /26 starting from the 22 gives you 16 networks of 64 addresses, which was enough for the 40, 25, 30, 10, 15, and in this case 5. Now they went ahead and used all /26s, so they're wasting a lot of addresses. This is a good lead-in for VLSM, which is my next video. VLSM, variable length subnetting. Variable length subnetting wouldn't waste 64 addresses here. You would only have 4 addresses here just by breaking this down to 27, 28, 29, and then you would, I'm not going to get ahead. You're going to go watch that video next. And then you would have 26s for these 5 networks, and then you would have 4 networks each /30s for these networks. And you would be able to so it says 26 is 16, 27 is 8, 28 is 4. It might be a /24. Let's see. No, 32 is 32, 64, 16, be 28, 128. 8. Anyways, you just keep going. It's a little bit more challenging. That's why they say it's more challenging to subnet when you're not on the octet boundary. All right, you actually have to do the math. You're going to go ahead and oh, there it is. You're going to do a packet trace of 11.7.5 subnetting. This is a challenging one because you have to create the network and then implement the network. And it looks like they start you out with a /26. No, I'm sorry. I'm still looking at the last slide for some reason. Anyways, so you will do this 11.7.5, and it's just a /24, so it's not too challenging. All right, well, that is my presentation. Again, that was just part 2 of the presentation. Let me go ahead and stop sharing. Hopefully that's helpful for you to understand. Even when I was learning subnetting, I found it challenging, but these videos I thought were really useful to understand the concepts, and hopefully you do too, especially with my added commentary. Now, that's the end of part 2. You still need variable length subnetting, and that's part 3. And that kind of ties everything together, takes it to another level where you're not wasting a whole lot of IP addressing. All right. My name's Lafond. If you have any questions and you're with me in NetAcad, ask your questions in the help discussion forum. And if you are watching this on YouTube, ask your questions down below in the comment sections. I appreciate that. Also, please like and subscribe. It helps me out. I appreciate it. That's all I got for you today. Again, Professor Lafond, it's been my pleasure to teach you today. Told you it'd be about an hour, and I'm about 10 minutes past. So sorry about those extra 10 minutes, but I'm done now. So enjoy your day and have fun subnetting.